Okay, I think we are ready. Welcome, everyone. Welcome to today's Yebo physics session. So I'm just gonna go over with you a few questions that I thought we should look at from Chat 9 on sound and superposition. Then after we do standing waves, I'm just gonna go over again and switch over to Chat 10, which is on thermodynamics. So anyway, I'll start with the first question that we see here, which is two speakers in an automobile emit sound waves that are in phase at the speakers. One speaker is 40 centimeters ahead of and 30 centimeters to the left of the driver's left ear. The other speaker is, so I'll just draw. So if head, that's 30 centimeters to the left and 40. So we've got one speaker there. And the other speaker is 50 centimeters and 120 to the right. So that will be 50 and 120. That's the other speaker. So that distance, according to Pythagoras theorem, will be 130 centimeters. And the other distance, that's a 3, 4, 5 triangle, that's 50 centimeters. Okay. So now the question goes, which of the following wavelength is or are in phase at the left ear for the speaker on the left and the right ear for the speaker on the right? So the wavelengths that will be in phase should be such that the distance between the speaker and the ear is a whole number multiple. So the distance, let's call it D, should be a whole number multiple of a half wavelength. So that's the condition to be satisfied. That distance from speaker to ear should be a whole number multiple of a half wavelength. So the values of n will be 1, 2, 3, and so on, integer values. N takes integer values. So the distances here are 50 and 130. These are the distances to the left and to the right, and the wavelengths that will have their half going into being multiples or factors, let me say, of 30 and 50 will be the following. So A is 10 centimeter wavelength. So 10 centimeters, the half is 5. 5 can divide into 50 and 130. 20, the half is 10. 50 and 130 are multiples, so that's okay. 650, the half wavelength there is 325. It can't divide in any of those values. So the correct value there is only the wavelengths listed in A and B, which is 10 and 20. So that's basically 10 and 20, which are the wavelengths that should have a complete phases, or that should be in phase for the left and right ear. Then question 35. Two tuning forks with frequencies 264 Hz and 262 Hz produce beats. And what is the bit frequency? So the question is, what is the bit frequency? So for us to get the bit frequency, FB is given by the difference of the two frequencies, which is 264 minus 262. So when two frequencies superpose or interfere in such a way as to give bits, the bit frequency is either given by the sum or the difference of the two frequencies. And in this case, the difference frequency represents the frequency of the bit envelope. So you've got two frequencies, F1 and F2. Something like this. So the bit frequency in this case is given by the frequency of the envelope. So that's the bit frequency. So this will be the first oscillation, which is due to the sum, and that one is the one due to the difference. So you can see there's a faster oscillation and a slower oscillation on that bit. So the bit frequency is 2 hertz. In this case, we have a bit frequency of 2 hertz, which is the difference between the two frequencies. And we have 2 hertz there. So there's 4, 2, 1, and 3, and 0. No bits are produced. So we actually produce bits of frequency 2 hertz. Then for question 36, two waves are described by, we have two waves described by y1 being 6 cos 180 t, and y2 being 6 cos 186 t, and are both in meters. So y1 and y2 are displacements of these two waves in meters. What is the angular frequency? Or with what angular frequency does the maximum amplitude of the resultant wave vary with time? So we also want the amplitude term for these two when they superpose. So the sum of y1 plus y2 will be given by a cos omega 1 plus omega 2 all over 2 multiplied by t, multiplied also by sine omega 1 plus omega 2. This one is minus, and this one is plus, all over 2 multiplied by t. So A is the, let me say 2A, if each have amplitude A there, 2A is the maximum amplitude. Then cos theta is the amplitude variation term. The nature in which the amplitude varies, and this one is the frequency term or phase term. The fast frequency and the slow frequency. So the angular frequency that would determine how the amplitude varies is given by omega 1 minus omega 2 over 2. So which will be omega for amplitude will be the value 186 minus 180 or over 2. This is 6 over 2, which is 3 hertz, 3 radians, actually 3 radians per second. 3 radians per second. So that's the 3 radians per second, which is among the given answers. So it's not the sum. The 366 will be from the sum there. So you should be careful for this amplitude term is due to the difference or the envelope that we looked at in the previous question. Then the two organ pipes open at both ends sound a perfect fifth such as 2 nodes with fundamental frequencies at 440 Hz and 660 Hz. Both pipes produce overtones. Which choice below correctly describes overtones present in both pipes? So the overtones for an open pipe setup, we have an open pipe like that. The first harmonic, if this is L, then L is equal to, this is lambda over 2. The second harmonic for the same length is when we have the wave like that. And in this case, this is a complete wavelength, L equals to lambda. So we know that frequency equals to V over lambda, which is V over 2L, because lambda is 2L there. So let's call this lambda 1. This is lambda 2, L is the same. So F2 equals to V over lambda 2, where lambda 2 is L, so this is V over L, and that makes this equal to 2F1. So already we can see the harmonics for such a pipe are such that Fn equals to N times F1, N times the fundamental frequency. So that means the harmonics or the overtones for these two pipes are such that we have, for pipe 1, the fundamental is 440. The first overtone will be 880. The second overtone will be 1320. The third overtone, so it's just N times F1, that's 1760, like that, and so on. And for pipe number 2, which is fundamental, 660, then 1320, then 1980, then 2640, something like that. So already we can see that the common overtones in both, at some point the fourth harmonic there, if we add 880 there, the fourth harmonic is at 440. 800, 2.2. Then the fifth is 2640. 2640. So already you can see that these overtones are common in both pipes. So which of the choice below correctly describes overtones present in both pipes? And the overtones present in both pipes are multiples of 1320. So that will be 1320, 2640, and 3690, and so forth, which makes D the most appropriate and the most correct of the answers that are given in the choices. Then question number 38 goes, which of the following wavelengths could not be present in a harmonic, as a harmonic on a 2-meter long string? So this requires our understanding of the harmonics, like we have just described in that question. And if we have a 2-meter long string, the harmonics can be the fundamental, the first overtone, and then the second overtone. Remember, it should be fixed on one end, so it ends on either side with a node. So always ends with a node. So this is lambda, This is, sorry, this is lambda over 2, 2 lambda over 2, which is lambda, and 3 lambda over 2. So these are whole number multiples of half wavelength. These are n lambda over 2, basically. So with n lambda over 2. So which means the harmonics that would fit into this 2-meter long wire are the wavelengths that whose half, the wavelength whose half is a factor of 2. So it would divide into 2 without leaving a remainder, or will need a whole number multiple or integer multiple to give 2. So in this case, one that will not be a harmonic, the first wavelength is 4 meters, whose half is 2 meters, so it will be the fundamental, so that is okay. The one whose wavelength is 2 meters is the first harmonic, is the first overtone, or the second harmonic, as it is called. Then the one whose wavelength is 1 meter, it means the half there is 0.5, so it will be the fourth harmonic there, which is 4 lambda over 2, so it's 2 lambda. So it's the one that has a wavelength of 1 meter. So it will have four antinodes. It will give us 4 antinodes, so that will fit. The 0.5 will also 0.25 because it divides into 2 8 times. So that's the other harmonic, which is correct. 0.89 does not fit because its half is not a factor of 2. So it's not multiplied by a whole number multiple to give 2. So that makes D correct, or the odd one out. So that's generally the last part of this session, which was looking at angular frequencies and harmonics within superposed waves in a string or in a pipe or in a standing wave setup. So I'm just gonna end this session for now, and we'll take a short break, then start a different session on thermodynamics in a few minutes. So don't go very far. We'll be right back.